Hi, my name is Mandy Peng. I'm the product manager from MySQL Heatwave on AWS.
Hi, my name is Nitin Kunal. I'm Director of Software Development at Oracle. Currently, I'm working on MySQL Heatwave engine development. So today we are going to talk about MySQL Heatwave service on AWS. We'll see how with MySQL Heatwave, we are able to achieve an order of magnitude faster analytics and machine learning processing. We'll also talk about OLTP performance and security benefits of MySQL Heatwave over other database services. So let's get started with the overview of MySQL Heatwave. So MySQL Heatwave is a single database for OLTP, OLAP, and machine learning. It is a fully managed service that provides benefits of MySQL transaction processing, extreme analytics processing without changing user application, and has capability of running machine learning training and inference without taking out data from the relational database. So here at Oracle, in our Heatwave team, we are constantly innovating and improving our service. In last 2 years, we have added a number of features to expand Heatwave capabilities and improve user experience. Data-driven optimizations, data management automation, reliability, and security has been our top focus. And as a result, now we offer MySQL Heatwave service on AWS. So let us see what MySQL Heatwave service in AWS looks like. So MySQL Heatwave is a fully managed database service in AWS. Data plane, control plane, console, everything is natively integrated with AWS, ensuring top performance and top user experience. And as expected, the service is loaded with capabilities like OLTP, OLAP, Heatwave ML, and Autopilot. And this is the only MySQL service out there that supports all these capabilities together. So here is an overview of Heatwave OLAP performance. So let us first take a look at Heatwave query processing performance when compared to database services like Redshift, Snowflake, etc. And what we are going to do is that we are going to take queries from a well-known OLAP benchmark, which is TPCH, and we are going to use 4 terabyte workload to do the comparison against other databases that we have in competition. So, and when we start running these queries, what we realize is that MySQL Heatwave outperforms Redshift by 20 times, Snowflake, Google BigQuery by 16 times, and Microsoft Synapse by 5 times. But since in cloud service world, every database service that we have may have a different set of hardware or compute requirements. So it is important to see how Heatwave, or for that matter, any database, fares on performances to dollar ratio metric. So again, for this comparison, we used TPCH queries and we used 4 terabyte workload, and we found that Heatwave is 7 times better than Redshift, an order of magnitude better than Snowflake and Google BigQuery, and 4 times better than Microsoft Synapse. So what we discover is that Heatwave is not only outperforming all the competition in terms of query processing performance, but as well it is the most economical database service out there. Okay. So what is the magic sauce behind this extreme performance that we are seeing? Okay. So the first important aspect of Heatwave performance architecture is the Heatwave data format itself. In Heatwave, the data is stored in in-memory hybrid columnar layout that enables horizontal and multi-core scaling and vectorized execution. Before running queries on Heatwave, the data is loaded from InnoDB, and during this load, the data is transformed from InnoDB format to Heatwave native format. And once the data is loaded in the Heatwave format to Heatwave engine, then queries are offloaded to the engine. So how the tables, which are the user tables which are loaded to Heatwave, that is structured. So the user tables are divided into partitions. Each partition is sliced into chunks, and within each chunk, we have contiguous memory buffers holding columns. The partitioning that we did for the user table, that helps in horizontal scaling. Chunks that we have created, that helps in multi-core scaling, and per column memory buffer helps in vectorization and cache-aware execution of the queries. And this hybrid nature of the data layout in Heatwave also helps in efficient updates or DMLs on the tables. The second aspect of Heatwave design is massively parallel architecture, along with hardware-optimized algorithms that we have built from scratch. So that a high degree of parallelism in Heatwave is facilitated by the cache-aware partitioning algorithm and data placement feature that we have. And together with data-driven query optimization techniques, we are able to achieve an extreme OLAP performance and scalability. So here are some query processing innovations done in recent releases. We are going to see how they are benefiting Heatwave and Heatwave query processing performance. So the first one in the list is Hypergraph optimizer that has been built and integrated with Heatwave in MySQL Heatwave service. So Heatwave engine is natively integrated with MySQL server. The logically optimized plans are passed from Heatwave optimizer for physical optimization to Heatwave optimizer. And since join order plays a crucial role in OLAP query processing performance, Heatwave now leverages the new Hypergraph optimizer that has been built and developed in MySQL engine. Hypergraph optimizer has been designed with multi-engine query optimization capabilities, and it takes the cost model and statistics as input from Heatwave engine and provides optimized join order suitable for Heatwave. So far, how the optimization was being done was the queries would reach MySQL optimizer. MySQL optimizer would generate logically optimized plan with exact join order that Heatwave should run. Now, there was no way of influencing the join order which was being generated for Heatwave in MySQL optimizer. Now, with the Hypergraph, we have a capability of doing multi-engine query optimization, and as a result, we are able to influence and guide the search space of join order optimization using the data-driven Heatwave statistics and cost model. Okay? And as a result, the plan quality improves. The queries start performing much better than they used to perform earlier. And in certain cases, the queries even outperform the handcrafted join order hints that user would have otherwise provided. So to summarize, there are like two main benefits of the Hypergraph integration with Heatwave. The first benefit is that the query processing performance in general improves, and the user doesn't have to specify complex straight join hints. And second thing is that it eliminates out of memory errors that we used to see because of poor join order. Okay? And in case if a query is found not to be suitable for Heatwave during the course of compilation, then the same query is rerouted to MySQL old optimizer for execution of that query in MySQL and InnoDB transparently without user doing anything. So here is an example. Hypergraph optimizer being a true cost model based optimizer, and the fact that it is not limited to the search space of left deep joins only, and with the help of the cost model and statistics generated by Heatwave engine, what we get is that much more broader search space. So as an example, the query that is shown here, query that is shown here, with an old optimizer, it would produce the join which we are showing, a join order that we are showing in the left-hand side of the screen. That's the best possible join order. Also, if a user wants to provide a straight join hint to force a given join order, this is the best join order the user could come up with. Now, with the Hypergraph optimizer and the cost model feedback that we get from Heatwave, Hypergraph is able to generate many more plans, including bushy join plans. And in this particular case, bushy join plan turns out to be an optimal or superior plan than the existing plan. So now we can take examples like we tried TPCH queries over 1 terabyte, and we learned that by enabling Hypergraph, not only we eliminated any need of straight join hints for join heavy queries, but at the same time, the queries outperformed their straight join hint counterparts by a significant amount. So query Q2, Q5, Q7, all of them outperformed the queries which had straight join hints, a manual straight join hints, when we compare it against Hypergraph. And that's one of the main benefits of Hypergraph, that it explores the search space automatically. It figures out what is the best join order and which is the most important or suitable join order for Heatwave, and it creates that join order for us. And once the logical plan is created, then the plan is passed to Heatwave, and Heatwave is carries on the physical optimization to create the final query execution plan, which then gets executed on Heatwave engine. Zone map is another performance feature that we added recently in Heatwave. And here the core idea is that to exploit information about clustering of data and skip a significant amount of data during filters and scans. So what does it mean? So let us take an example of a table with one column as a primary key column. Now, by default, the primary key columns have sorted order. These columns are already sorted. They're pre-sorted. Now, can we take advantage of this information that a given column is sorted when a filter or a table scan operation happens on that particular column? So answer is yes, we can do that. How? Through zone map. So what we do is that every time a table is loaded, we compute min and max statistics for every chunk of that table while they are getting loaded to Heatwave. So in every chunk, we figure out what is the maximum value and what is the minimum value while hiding behind the load operation that is going on. And now during query processing, we use that min and max statistics and compare that against the predicates which are present in the queries to skip or to prune out these chunks which do not qualify the predicates of the filter. And as a result, depending upon the data distribution, depending upon the predicates that we are using in the queries, we can skip a significant portion of our data while doing query processing and thereby improving the performance. Particularly the range queries or queries which are more towards point queries, they significantly get benefited by this optimization. So here is a study that we did. So we took 1 terabyte of TPCH data, created a filtered query on one column, and this column happens to be a primary key as well. That means on this column, MySQL already has an index built on it. Now in this graph, in this chart, what we see is that we are varying the selectivity of the filter query that we have picked in a way that it starts with a point query, it returns only few rows, and then in other extreme right-hand side, it returns almost all the rows which are present in the table. So we are moving from point query to full scan. And what we see here is that Heatwave without zone map used to perform almost similarly, whether it is a point query or it's a full scan, because Heatwave by design is built to do a full scan as fast as possible. So the blue line shows the performance of Heatwave. Now, the yellow line shows performance of MySQL. Now, MySQL is using index to do this filtering. And if the queries are point queries, or if the queries are returning only few rows as a result, then index can be very efficient and the queries can return really fast or complete very fast and have very low latency. So that's why the yellow line, we see that towards the point query, it's really low. And for the full scan queries, it is really very high, orders of magnitude higher. Right? So now our goal was that can we reduce or can we bring down the blue line of Heatwave down further by doing certain optimizations? And zone map is the answer. So now with zone map, the same query, when we run the same range of queries, then what we see is that for the lower selectivities or the cases where the number of rows being returned from the filter is small, we have significantly improved the query processing performance, almost by 10 times. Okay? And also by doing so, we have moved the inflection point from what point Heatwave starts becoming better almost by 7 times. So the older inflection point used to be around 0.05% selectivity, and we have moved it back to 0.0075%. So it's a big improvement, and that helps especially the mixed workloads where we have a mix of OLAP queries and range queries and sometimes point queries as well. So Heatwave now can be used for more variety of queries by doing this optimization. Another important optimization that we recently included in Heatwave engine is late decompression. So in Heatwave, the data is compressed using LZ4HC algorithm before the data gets loaded to Heatwave engine. And this is to make sure that we optimally utilize the memory that is available in Heatwave servers. Now, during query processing time, the data which is compressed has to be decompressed before actual processing can happen on the data. So the table scan node of Heatwave query processing engine starts decompressing the data, which is the columns which are needed, and then on top of that, it applies filters, joins, or whatever operators are included. Now, with this optimization, what we did is that we decided to decompress columns only when they're absolutely needed by a query operator. So delay the decompression as much as possible. So how does it help? So in the base case, we were decompressing everything, and then we were applying filters or expressions or any other operation that was needed. However, in the late decompression case, because we are delaying everything or every kind of decompression to the last minute, what we achieve is that it may be the case that on those tables, we have heavy filtering, and then we are decompressing only after filtering, as resulting into compute being spent only on those chunks which are needed by the queries. Okay? So if the decompression is applied after the filter, we are saving the decompression compute cost on all the chunks which have been skipped by the filter operator, and thereby we save a lot of time, and hence we get the performance gain. And when we tested this feature with TPCH queries, 4 terabyte workload size, we saw that total time almost improved by 20%, and the average time improvement was around 11%. And as well, we have seen that such kind of optimizations are giving even better returns when the queries are heavy on string column processing, because for a string column processing, the cost of decompression is even higher when we compare to other data types like integers. So that brings us to Autopilot capabilities that we have in Heatwave, and we are going to talk about how Autopilot capabilities are helping Heatwave query processing performance. So first in the list is auto query plan improvement. So both logical and physical query optimizations rely heavily on cardinality estimations in any database, particularly in Heatwave, where we are doing very aggressive optimizations, such as cache-aware hash table sizes or cache-aware partitioning algorithms and such. This becomes cardinality estimation accuracy becomes even more important. The traditional methods of estimating cardinalities are error-prone, especially if we have a lot of joins in the table. The error percentage thus just multiplies as we go up in the tree of a query plan. The intermediate relation cardinalities of all the queries executed so far are cached in Heatwave statistics module. As an example, the intermediate relation statistics of for A join B join C are cached in some hash table which has been shown here on the slide. Now, when a query contains A and join B, some other query that contains A join B appears, then the exact cardinality from the previous run is reused to do the optimization. And thus, the new queries with exact match or subset of match use 100% accurate cardinalities, and thereby we improve the performance drastically. So with this technique, the systems get better and more as and when we are running more queries. So with time, the system is accumulating more knowledge about statistics, more knowledge about cardinality, and it is getting smarter and smarter, and it is helping both the logical and physical optimization even better. So now with our test setup, we have observed that for TPCH workload and TPCH queries, with this, by enabling auto query plan feature, we were able to improve the performance almost by 40%. So the next set of feature, the next auto feature in our list is auto scheduling. So usually analytics query run longer than OLTP queries, and thus mixed workload cases, it is important to keep the elapsed time of the short running queries in check. Otherwise, short running queries will always be queued behind long running queries, and they will get starved, and eventually they will start taking much more time than user is anticipating. So we solve this problem by auto scheduling. The idea is to reduce the wait time of short running queries on Heatwave without significantly increasing the elapsed time of the long-running queries. So what we do is that in Heatwave, we are able to predict execution time of each query, and then we use that information to automatically reorder the queries such that shorter queries, they get ahead in the queue and get executed. And while doing so, we take care that the long-running queries, they are not starved beyond certain limit. So, and as a result of this, what we observe is the short-running queries their elapsed time has reduced significantly, but there is a very slight increase in the elapsed time of the long-running queries. And this example of TPCH demonstrates that. So here we are using TPCH queries. We have classified them into short-running and long-running queries. And once we enable the auto scheduling, what we observe is that the total elapsed time for the short-running queries almost improved by 45%. However, the wait time or the elapsed time for the long-running queries increased as well, and that increased only by 6.6%, which is nothing compared to the amount of time usually the long-running queries take. So as a result, we are able to support the mixed workloads of customers much better than we were without the auto scheduling. So the next feature in the list is auto data placement. So in a Heatwave, we rely a lot on partitioning the data and then doing the query processing operations independently in each of the nodes and then independently on each of the cores. This helps in achieving extreme parallelism, and it helps in reducing the contention related to synchronizations that can happen if we don't partition. So we heavily rely on partitioning operator. However, partitioning operator during runtime can be a costly operation because it involves shuffling the data over the network. Network can be unreliable, or network can have other types of contentions while we are doing query processing. So how do we avoid the problem? So we have a feature in Heatwave that's called data placement. So what we do is that while loading the tables to Heatwave, users can pick that for these tables, these are the columns that can be used for pre-partitioning the table. Okay. However, selecting these right set of columns for pre-partitioning is a hard optimization problem because it depends on several factors. It depends upon the knowledge of system, how it works. It depends upon what kind of workloads we are running. And there can be competing factors that will make the decision by hand or by end users very difficult. So we solve this problem by using machine learning based prediction. So what we do is that auto data placement uses user workload and data properties of the users to predict optimal keys which can be used for pre-partitioning the table. Auto data placement can also predict the amount of improvement that is expected in a given workload. And when we started testing it with TPCH and TPCH-like workloads, what we found is that the improvement in performance and scalability was up to 37%. And this was very consistent with all the other similar benchmarks that we tested.
Thanks, Nitin. So now I'll talk about our machine learning performance. But before I go to talk about our performance, I want to just give you a high-level overview of our machine learning Heatwave ML. So similar to analytics that Nitin was talking about, we have added machine learning to MySQL Heatwave. So very similar to the advantage of analytics, the same thing happens for ML. This is an in-database machine learning, so you can train, inference, and predict and explain the machine learning for your application or for your user. The other thing is that since the data is already stored in MySQL, so you don't need to ETL the data into a separate ML environment for doing machine learning training or inference. And then also because we use the same Heatwave cluster for machine learning, we can use the multi-node and then inter-parallelism and intra-parallelism among the Heatwave nodes to achieve better performance than all of our competitors. So we support two types of algorithms, classification and regression. So I want to show you here is that we have a set of data that is a good representation for enterprise use case. These are all well-known benchmark data sets. And we use these data sets to run machine learning training against Redshift ML. So in a typical machine learning lifecycle, training of the model is usually taking a much longer time than inference. So in here, you can see out of all of the data sets that we use, Heatwave ML on AWS is actually running faster than Redshift ML. And for the ones that like on Redshift ML that has an X, that means that they can't even finish within the 90 minutes time frame. So that's X there. As you can see it here, on average, we are 27 times or 28 times faster than Redshift ML. Looking at regression, we have another set of data sets that is also enterprise data sets that you can find it on our GitHub that is published there. With regression, you can see it here as well. Heatwave ML is actually much faster than Redshift ML, and similarly is about 26, 27 times faster. So why can we run much faster than our competitors? So as I mentioned earlier, that we make use of the Heatwave cluster so that we can exploit all the Heatwave ML pipeline with the intra and internode parallelism. So we can run the job in parallel within the node and among the nodes. And we can run the ML training in one single pass. How can we do that? Because of the intra-parallelism and also because of the parallelism, and also we evaluate multiple models in parallel. In Heatwave ML, we automate the machine learning life cycle so that you don't need to worry about like getting into like data pre-processing, algorithm selection, adaptive sampling, feature selection, or hyperparameters tunings. So all of this is done automatically by Heatwave ML. And one of the things that we do is that we highly parallel the hyperparameter tuning so that it is much faster. Also, when we are looking at the data for training the model, we do adaptive sampling. So we don't need to scan all of the data, and then at the same time, we don't lose the accuracy of the data. And then eventually the training converge, and then so that's why the training can be that fast. And also the machine learning Heatwave ML also scales with the cluster size. As you increase the cluster size, your training time will also decrease. So besides machine learning performance, we also want to talk about OLTP performance. And MySQL has been the most popular open source database among developers. As you can see here from Stack Overflow and JetBeans, MySQL has been the #1 popular database among the developers. And MySQL is used among all the innovative organizations. As you can see it here, MySQL is used in all of the in the social area, in e-commerce, in finance, and then in manufacturing. And you can see that there's a lot of this, all the innovative companies such as Facebook, Bookings, Netflix, Tesla, they're all using MySQL for their customer-facing application. So there are two new features that we're introducing on MySQL Heatwave for OLTP. So the first feature that we are introducing is auto-thread pooling. This is part of the MySQL Autopilot, which is using machine learning-based automation for improving the overall system performance. So for this particular auto-thread pooling, we actually make the OLTP performance faster by controlling the execution of transactions. So without this feature, all the transactions are coming in as a non-uniform. The connections are non-uniform. So that's a lot of the time there can be like some long running transactions, and some of the transactions will need to be blocked or wait behind those long transactions. But with auto thread pooling, we make sure that the transactions can be controlled within a thread pool, so that all the resources is used in a similar way, and then the transactions can be it will not be blocked by long transaction. So here is the from our test result using a TPCC, which is a well-known benchmark for OLTP. With a 10 gigabyte of data, you can see it here that when we are comparing with Aurora, with MySQL Heatwave with the auto thread pooling, as the concurrency increased, you can see that our throughput has been able to maintain. And then at the point of where concurrency with 2048 concurrency, the throughput is actually 10x better than Aurora. Another feature we have introduced is the auto shape prediction. So in OLTP, it's not easy for user to predict or decide what are the shapes or the compute shapes that they want to use for their workload, as their workload can change over time, right? So in e-commerce, for example, there can be a spike in Christmas time or all the holiday times. So during that time, usually it depends on the user experience to adjust the resource on the compute so that they can accommodate the spike that is seeing. So with auto shape prediction, we collect the statistics from InnoDB, from the query matrix, and from the trace and logs that from the MySQL. And then we have a machine learning model that can use this matrix to predict the right size for the workload that we have been seeing, and predicts the size. So from here that we are using with all the benchmark that you see on the left-hand side, so we are able to predict the right size. So for example, on the first few rows, when so originally the compute resource is using a 2 vCPU and 16 gigabytes of memory, and when the workload changes, we predict that the compute resource should be using like a 8 vCPU and 64 GB of memory. And once the instance is upgraded, you can see that on the right-hand side, the result has been improved, right? The throughput improvement, and then the buffer pool heat rate has been improved. On the bottom side is that we started with a bigger instance with the 8 vCPU, 64 GB memory. And as the workload changes, we suggested for a downsize to a 4 vCPU and 32 GB of memory. And then you can see that's the improvement in the throughput. And then also you can see a better buffer pool heat rate. So besides all the performance that we have done for MySQL Heatwave, for OLAP and machine learning and OLTP, we also has improved the security of the service. So one of the things is that the data is always encrypted inside the service. You can see it here that the data is encrypted when it's stored in MySQL at rest and also in transit. All the communications between the nodes are encrypted. And the other thing we have done is also enabling a few MySQL Enterprise security feature. So the first one is the data masking. So you can use data masking on MySQL and also with Heatwave, and then you'll be able to mask the data. This is especially useful when you have a PII compliance requirements that you can mask all those sensitive data. The other thing is asymmetric encryption. So you can also encrypt the data that's sensitive data that you want to encrypt, so that your end user will not be able to see it. We also have enabled the MySQL SQL firewall. So now you can use this feature to block any unknown SQL statements. Besides that, we also have like very strictly administrative privilege, so that will prevent user from power use from so that we can provide better security for the service. And since the service is built, managed, and supported by MySQL development team, we'll always provide the latest security patch, and then the service is always on the latest version. And the last but not least is that we support multi-factor authentication as well. So with that, I want to conclude with a summary of the service. So before we go there, let's see what the customers say about the MySQL Heatwave on AWS. So we have a list of customers who has tested our service before we go GA. And all of the company, as you can see here, this is just a small numbers out of the list there, is that they are seeing significant improvement in performance. And this is all thanks to all the features that we have just described. So in summary, we are 20 times faster for analytics, 25 times faster for machine learning, and 10x better OLTP throughput. So thank you for your time. I will conclude the session now.